Hello everyone, welcome back to Cloud Computing and Big Data, Lecture 3 about Apache Spark for Cloud Applications. This is a lecture which nicely connects to Lecture 2, which were a little bit more a 10,000 feet perspective on how we use Apache Spark in MS Azure, how we use Apache Spark for machine learning, but we didn't really look inside Apache Spark. We did a couple of Python lines in Jupyter notebooks, and from this we basically started to do some machine learning. We did evaluations, and parts is also in the assignment from you. So I think you got essentially the feeling, but now what we have to really understand is how Apache Spark works. And then in the complementary practical lecture 3.1 that will come on Thursday, we will go more into practice, how that really works with the different capabilities of Spark. So before I go into the material of this lecture, so let us look a little bit what we did the last time. And we started with really machine learning fundamentals. I said also, it is not really a full course on machine learning. If you're really interested into this subject, please go and sign up for the machine learning course we have here at the university, or take a course at Coursera. There are also lots of YouTube lectures if you like for machine learning and so forth. So please make sure that, of course, what you learn here is just really the kind of small tip of the iceberg, if you want. And we started with a very, let's say, fundamental aspect of classifying roughly the techniques of machine learning, which goes roughly into classification and clustering and regression. And we learned a little bit that data mining has some overlap. So you would see things like mining data in terms of association rules, shopping behavior, is partly also machine learning, although it's more data mining. But however, these really overlap. And the same is true for recommendation engines. So this is something we will look in on Thursday, where we will basically see a little bit how Netflix and all of these work in analyzing big data in order to give recommendations to user, and which are in fact personalized recommendations. However, the key ingredients we had for machine learning was really the three things. You know that from the beginning. So there must be a pattern. And we believed here, for instance, in this iris interesting flower setup, we believed there is a pattern, and it was actually true. When you look at them very intensively, you will see that the petal and sepal actually differentiates. So the flower shape essentially is a little bit different, although of course a human here would maybe here and there has some trouble to really identifying, is this now iris setosa or iris agenica? So there's a pattern to discover. There's also no set mathematical formula. There's no one telling us in physics now and says, okay, this is an established law of physics, how you differentiate iris setosa and iris agenica. There might be other methods how you do this with histograms of colors and all sorts of things, but the real mathematical formula, like we would say maybe in physical laws that we then use for numerical methods to approximate something like this, is not really existing. So that's why we also go for machine learning. And of course, the third ingredient in our flower setup was kind of important, but is important for every machine learning that you have, because machine learning essentially means learning from data. And without data, you're in trouble. And of course, the quality of data is a key ingredient. So not every data and every big data means it's just perfect data, and the better the data, it's really something where you have to look into the data, as we saw the last time and a couple of lectures ago, with pre-processing, looking to the data, understanding the data, understanding noise in the data, and so forth. So then we actually looked at some of the most earliest machine learning models you can find. And this is interesting because it is still fueling neural networks today in a, let's say, more advanced fashion, of course. But here you see a neuron, essentially, that was developed in the 50s and called the simple perceptron model. So you see, basically you have this signal X going in, which is essentially different pixels of a flower, could be also sepal and petal width and length, as we had in our lecture. And we put this all sum up linearly using weights. That makes it a linear learning model, linear, right? Because there are highly nonlinear methods in machine learning that we don't cover right now. And we basically summed them up using weights. We had the bias that is always there, but we also said, like, at the threshold of a line we play around with here on the right-hand side, we can always learn that as well. So we put the bias essentially in the learning itself. And with this, we come to this very interesting formula as you see on the top. And then we take the sign. That was very sufficient for us. It was +1 or -1, saying essentially, is it this type of class or is it that type of class? Now, that is a very easy assumption, admittedly, and it's a binary classification, which means just two classes. And when I do research here with some of my PhD students, we have, let's say, 50 classes. We have 42 land cover classes of the Earth. So not only just two classes, and the more classes, of course, the more challenging essentially it is. And of course, this means that some of the models we have here for binary classification will not work anymore. We need more sophisticated machinery, like neural networks, like decision trees, like different methods you will find now in deep learning for it. So things we will all cover step by step throughout this lecture. So let us stay a little bit in the realm of linear learning models. And the linearity here is very much important to understand. It's in the weights, right? All we think about, it's about the coefficients we want to learn, because X is constant here. X is our data set. We have that already. And we have Y, which was our label usually, because in the last lecture we said we focus on supervised learning. That means we have a label Y that tells us a little bit about the quality of our hypothesis that we have here, H of X, a specific hypothesis of, say, taking the sign from the W transpose X, which was nothing else than the dot product, or a very compact notation that you see up there. And what you do is you play around with this line until it fits and the error gets less and less. Now, with the perceptron learning model, there came the perceptron learning algorithm. You remember this hopping of the line very drastically by subtracting and adding a vector. But of course, take away the message that this is really a very simple learning model and has a lot of assumptions, like, for instance, linear separability. And you will find that going to really practical problems more and more, there's no linear separability in practice. So we have to have other more advanced methods. So in one of these advanced methods, when we had our Chicago restaurant food inspection example of the applications that you also tackle partly in the assignment 1, we picked the logistic regression model that does actually remain in the basically models of linearity, because linear in the weights, but it adds a nonlinearity to it with the sigmoid, or also the logistic function. And we will come back to this today a little bit, looking under the hood, although in practical lecture 3.1 that we have on Thursday, we will look much more on the gradient descent and optimization problems that are actually fueling this particular classification model. But we have seen that actually using machine learning in a cloud like Microsoft Azure, where Jupyter is there, where Apache Spark is pre-installed, we use PySpark, we have a Spark session, and create a simple pipeline. And in a couple of, let's say, lines in Jupyter, we already have a model. What we had done before was essentially a lot of work, massaging the data, preparing the data. There were lots of columns. And let us come back in this lecture a little bit around this. And by this, we also will learn more about Apache Spark in general. So this lecture will really be, again, something about Apache Spark, the design goals. Why was there Apache Spark? A key ingredient of Apache Spark under the hood that we didn't really look at the last time, which is a resilient distributed data sets, a real interesting concept for fault tolerance. And I will give you some examples. And then there are two key notions of transformations and actions in Apache Spark, which are quite useful. And then we will basically look a little bit around a comparison of two technologies like Apache Spark and Apache Hadoop. Hadoop was way before doing parallel and distributed computing, but Apache Spark really made a key difference, and we look into this by really reviewing what it means to have in-memory execution, but also looking not only on the application side, of course, looking on the cost side as well, if you want to really run it in your company, let's say renting resources from the Amazon Web Services in the cloud. So this is an important part of this lecture. The second part will be much more about the ecosystem around Spark. You will see that Spark per se is already interesting, but of course it also lives in the community because there's lots of different libraries that really make advanced applications possible. It has a very good support for the structured query languages. For all of you that had databases in relational databases, courses or things like this, that should mean something to you. It's a very, let's say, established technique to get data out of databases that are mostly in the relational database fashion. You have a machine learning library. We will talk a lot in this course, but also here today in this lecture a little bit. And then thinking about that there are new applications more about streaming, where I said in one of the lectures, you know, the problem is not necessarily always a volume. It could be the velocity, the stream, the kind of, you know, fast running data that we have to filter, that we have to analyze, like Twitter tweets, right? You want to analyze for your startup how good you are in social media, how is your product in social media. We will have an example of this. Then also graph libraries will play a huge role, not only here basically today, because I give you an interesting, very known example of an application called PageRank, which you can solve nicely with it. Also in subsequent lectures, we go back to graphics when we have, for instance, social networks on Facebook. They rely on graph databases. It's a very growing field, a very important field of, let's say, dealing a little bit more with unstructured data, while SQL, relational databases, deal very good with structured data, but unstructured data is something where you have lots of sparseness then in the, you know, SQL or relational databases. So you need something different. And if you have lots of interconnections, like a friend or friend that likes something and stuff like this, like Facebook and other social media, then you essentially need another data structure. So it's also interesting that Apache Spark provides this also natively on top of the core. And then we basically look here and there, of course, in machine learning applications along the way. I also brought up a little bit shortly Google Colab, although there's more a video about it. I will show the exact idea about it, but essentially we'll learn more and more. It's not new. It's a Jupyter notebook essentially in the cloud. This time it's a Google Cloud. And there's also the possibility of using PySpark for it. So you have quite some flexibility. If you're running things with Spark, you can put it to MS Azure. You'll see it has support in Amazon Web Services, or you put it to Google Colab. I also would like to highlight some of the business applications, because that's really the open community of Apache Spark that lives within this. And there you see it's really a growing business. There are Apache Spark Summits. There's a new release, Apache Spark 3, which shows you some momentum of these technologies. Although many of the examples we do is still based on the old version, you see with this that there's a growing interest, and it's not a dead open source project. Quite the contrary, it's much more one of the most active ones. So with this, we actually fill a lot of promises, which is quite impressive on the right-hand side. So you see also with this, how intertwined really now cloud computing in lecture 2 was with this lecture 3 here. As I said earlier, we just did lecture 2 a little bit on a 10,000 feet perspective, just using this Python lines, but don't really understood what's happening underneath, right? So where is the data? How is the structure of the data? What is a worker? What is a head node? And things like this. We all will clarify all of these throughout this lecture today. So fasten your seatbelt and we go to the basic Spark capabilities. So this is really on thinking about, again, when we're thinking about lecture 1, there is a big data impact here that's essentially saying we need something where it needs to be scalable. Data is growing more and more. And with this, we accumulate data more and more. And once we have accumulated lots of terabytes of data, let's say in a company, data about your customers, about social media, you know, maybe grab every now and then about your products, whatever data it is, maybe also even just likes or, you know, recommendations from your company. This is things which you accumulate, and suddenly you have a big pot of data. Now, putting this big pot of data into the web and transferring it all the time is of course a different issue. So in this sense, it makes sense to think a strategy about clouds upfront where you accumulate the data, so that you kind of, instead of moving the data to the compute resources you have, like high performance computing centers and so on, you directly would say rather move basically the computing to the data in a way with cloud computing, that you accumulate the data in the cloud and the computing comes just naturally with it. Of course, here and there you will still transfer, you will inject data into the cloud, and you will see also in subsequent lectures that this costs as well. But of course, this is something to think, that a traditional model where you come, transfer a lot of data then to high performance computing systems here and now and then is a little bit unfeasible. In fact, nowadays, sometimes people even think of putting a lot of hard disks in a truck and then actually drive the truck to a high performance computing center. It's much more faster than migrating or transforming lots of terabytes of data, or even petabytes these days, to a dedicated high performance computing center. So with this, there was a need for really having a new programming model, and also the complexity that you had with traditional models using SSH a lot, using parallel programming yourself. And the complementary course, HPC is all about it, right? So we program MPI, we program OpenMP and things like this, where you learn really parallel programming, which is hard. It's not like serial programming. It has concurrency. It is not easy to program that way. In this sense, there was also a need to make it easier, right? So it's a programming model that abstracts a little bit from this parallelization, where you have, as we did in lecture 2 last time, just a couple of Python codes, and the magic is actually underneath. And this magic we want to uncover today. Just a short remark, you will see that again, this lecture is highly intertwined in another technology called Apache Hadoop. Hadoop has also not only a computing model called MapReduce, it has also a Hadoop distributed file system. So these are things which kind of naturally would come partly first. However, from the learning of the different years we teach this now, we found also it's important to start with assignments early. That's why we start with Apache Spark a little bit from the 10,000 feet perspective, and we'll now go little by little over the course of the next lectures while you do your assignment in deeper understanding what Hadoop contributes to Spark. You will see that lecture 5 will be all about Hadoop distributed file system, but also about the MapReduce systems. And with this, you understand then fully also Apache Spark. So here and there, I will not cover everything today, which is about Hadoop, but focus really on the Spark ingredients, right? And this is something which this is also explaining when you look on the big data analytics frameworks. In a way, Hadoop was first, a so-called MapReduce that we had also in the earlier lectures. You break up a problem in small ones, which is called map. You do a kind of grouping, shuffling, sorting on the data, and then you reduce it to again, having, let's say, a problem tackled and get some conclusion. So divide and conquer, if you will. But this was really done on distributed file systems, on files, and it was really successful at that time. But of course, think about now that in memory, we learned in one of the last lectures, is really very fast for computing. So this model, like Hadoop, was actually neglecting this fact a little bit. So in this sense, Apache Spark really focused on the implementation of in-memory processing. And we will explore this again and again. There are also new ones like Apache Flink, others actually that come along that maybe much more leverage the memory of hardware that is existing than just the traditional Hadoop approach. Of course, both are in a way still intertwined also because of the distributed file system, but this is really an important consideration. And this is something where we then see on the right-hand side here, the logistic regression as an example. When you compare it just roughly Hadoop against Spark, you will see that the running time is enormously faster for a simple, let's say, classification model like logistic regression. So the Apache Spark basic properties really are that it's basically an open source project. It is very active in the open source domain. You will see here on the right-hand side the general setup. It has basically worker nodes which execute tasks and have, of course, cache. The cache comes now with the memory part of it. That's why it's quite important to mention. So the cache is, of course, limited, which is then one of the pitfalls of Spark. I will elaborate later on in one of the slides. But take away the message that this makes it now very scalable, that you can add more and more worker nodes to one problem. Of course, you need a cluster manager. So it depends again on how many CPUs you have, maybe GPUs you have if you distribute a deep learning training. But a cluster manager kind of manage your resources and can steer then how the work is actually broken into smaller parts and then distributed across a cluster. Then we learned in one of the earlier lectures the Spark session and the Spark context, which is really how you start essentially, which is partly also known as a head node, basically then steering lots of different worker nodes and managing all of this. So we will come back to this again and again. Now, when we think about this traditional MapReduce model that we have in Hadoop, and we will explore this together in one of the next lectures, this is more really towards directed acyclic graphs, if you look at it. And there are lots of data sharing capabilities and in-memory computing, which is going alongside. And the key concept really are the RDDs and the usabilities. They are fault tolerant. They basically operate all in parallel without you knowing. You see there on the right-hand side an example. When you want to filter a message from a text file, you have with Lambda small functions you can implement, and actions here you see splitting and contain every line basically in the text file that has an error message. If you want to have a log file analyzed, it's one line. You say text file dot filter, and on this dot map in this regard to have /t to have the end of the line. So essentially come to these RDDs that are created underneath from the source code that you see there. Hadoop, because of the file system, you have a text file, so you have to access the file system. You create a filter, so you have a filtered RDD, and here you create a small kind of pipeline already if you want, or a kind of small lineage of this RDDs, which you actually implement very beautifully in Python, and you don't know really about the underlying fact essentially, right? That this is kind of a graph structure. It scales then with this enormously, adding more and more worker nodes to it, and then distribute this also automatically, which is explained here a little bit. You see that here, that of course the graph has a benefit. It's not only map, do something, reduce. Here you could have things, different things in parallel. You see here stage 1, stage 2 might be different ingredients of feature extraction, feature engineering methods that you would have for essentially a machine learning problem, and then later on you do the machine learning problem. So it's very usual to combine different things. And then you see that here the RDD usually takes away lots of caches and tries to use cache and memory where possible. But of course, if it's basically limited by memory, right? So it could not fit maybe all the time in the cache. But also by having already this possibility to put a lot of things in the cache, the RDDs really have a good chance of being much more faster than putting things to disk and back and forth like Hadoop is doing. And even if there's a rebuild basically on failure aspect, it will actually wait and see that one of the stages, for instance, that you see here will be then finished computing, and then will automatically restart failed jobs in this cluster, and then we'll connect them again to this graph. So it's a very fault tolerant solution, which actually stand the test of time and is now extremely stable. In earlier versions of Spark, that wasn't the case, but nowadays you can really assume that this works very nicely. So for the RDDs, there are kind of two important aspects to it. Transformations is quite important here, which are examples here that you really transform a sort of data structure that you see here. You see here on the left-hand side, we have the nums, which are numbers, and you parallelize this. So that means now it lives actually 3 times, right, in different slices in this array. It's not really one array, it's really 3 different areas having 1, 2, and 3. Then with this map function here from the nums, from the numbers, you can use now this RDD with this very simple function, which is just taking here actually the square, is 1, 4, and 9 on all the different entries, 1, 2, and 3. Right? Now take away the message that you directly assign this to the squares. So the squares have now 1, 4, and 9, which is also very beautiful. So quickly you can have functions and the result is directly in another RDD and meaning already in memory. So there's no point of now dropping this to disk and restart a job by filtering maybe all those which are dividable by 2. Basically, and this would be only 4, for example, and you directly say that's even, and again assign it. And it's again in the memory. So, and this is exactly how Spark works. It leverages its memory aspects, even if it's underneath, of course, in different slices and different parallelization. But you don't see any of this. It is automatically done by Apache Spark with downscaling and upscaling, depending on how you configure the worker nodes. In the end, just a flat map with showing another one with an interesting function. But I think this is very self-explaining anyway. But it's very interesting to embed this and having a kind of aspect of it that is really parallel. And here are the actions where you have a similar aspect, but you parallelize everything, but now you want to collect something. Basically, you want to have it as a local connection again, right? So that means you have it often distributed, but if you want to have a local result and write it to disk, finally, you want to maybe have it on one node. You can take different elements of a data structure. You can count the number of data structures. All this is, of course, better when I do some practicals on Thursday. Just shows you the power of RDDs, really. And especially here, you can also save as to file. Here's a little bit of downfall. If you drop things to disk, it's getting slower, right? We leave the area of memory. And we will see that in a minute, why that is so crucial. The point is that if you compare now Apache Hadoop and the initial setup, what MapReduce was standing for, and if you do these iterations of machine learning, let's say like logistic regression has an optimization problem alongside it, it really means like going through lots of HDFS read. So you read the data, you do an iteration like a map function, and then you drop it to file, do an HDFS write. And this is, of course, always very slow. Then you have the, let's say, reduce function. You did something with the data, or you want to do something again with the data. You read it again, write it again to disk. So the result will be there, but it's much more slower. Apache Spark has a very slow starting. Reading things from disk is the same problem like Apache Hadoop has, but it will try to use in each of the different iterations in machine learning, in MapReduce, whatever application you have, to really use the RAM to the most significant degree. And that's why in our example here from HD Insight in our lectures, this is just incredibly fast, right? When you compare to Hadoop, which really then had to work with a Java-based HDFS system and being very slow. So this brings you to the idea of, okay, when all people say Apache Spark is so brilliant, so much faster, why on earth should I use Apache Hadoop for stuff? And I think one of the ideas is looking at the prices here. So this is really cutting edge Amazon Web Services. And if you think about, you need cloud resources that underpin, of course, your Apache Spark, which is just software, it's hardware, right? And when we look here, general purpose, for instance, is just $2 for a really good 256 gigabytes memory and good storage. You go there for memory optimized ones, which are really big data, right, with 3.9 thousand gigabytes, then you go there and have $26 per hour. So you see quickly how this is rising. And this means the more memory you have or want to have and data, this costs you a hell of a lot of more. So, and if you don't do this, if you here start with the 4 gigabyte one, where you pay only a couple of cents, yeah, you go the price. There's no memory enough for Apache Spark. It will be almost like the performance of Hadoop. So this is, of course, now the downfall of it, if you want. You need to have memory available for the software. And if you go to the cloud, this will cost. In one of lecture 1, I think we talked about that RAM is very costly these days. And in a way, it's still the bottleneck today we have, because this is nicely fast, but it's incredibly expensive. Normal storage like SSDs and so on are comparable cheap these days, but really it's a problem of thinking about the memory. And you see here was an example of Amazon. And if you go to Google and others, it's the same way. They all cost much more. Just think about some distributed operations again, because of course we want to scale out, right? We want not to be in the cloud to remain on one node. Again, you see on the right-hand side what we already know. There are different worker nodes, and you see this illustration with the red box here, which illustrates compute nodes. You would say you have one head where the Spark context and the driver program is, but then really the cluster manager can assign more and more worker nodes. Of course, you can configure this also in your environment if you will, but this is really a dynamic aspect, so you can have a scalable solution to your problem. This is always not so simple, but essentially all of this is taken away from you directly. You just program essentially in this RDD objects, and then essentially the kind of underneath framework of Apache Spark put this in a directed acyclic graph scheduler that then split all of these RDDs in different parallel entities which are independent from each other, could run in parallel, for instance, these stages, and then have another stage where data is needed. So it kind of optimizes your execution while you just provide one line with join, group by, filter, count, and whatever, where this would be maybe in Python. Then underneath, a lot of things are done in Apache Spark in order to have really executions in really concrete tasks, which are then even can be broken down in different threads. And of course here, the thing that we leave a little bit out, you see this in the kind of illustration in the middle, HDFS is there, right? So there the data perspective comes in, which we also will explore a little bit more in lecture 5 then. So we summarize: cache is important, partitioning is important, automatically done by Apache Spark. Thinking a little bit about the dependencies, you have transformations, you have actions, which are really more real results on the data. So, and all of this is done in distributed fashion. Also in lecture 5, we will look deeper in Hadoop and also its yarn scheduler to have MapReduce jobs, which also partly Spark is relying on. So you have here basically a client like your laptop that goes to the cloud, and then the resource manager that is actually scheduling the jobs on these different server entities. So this is something where you have to think about, of course, it's real hardware. There are different multi-users that want to have the same server. So there need to be a framework that is also looking on this and also scheduling and have an overview what data nodes are used, to have an overview what free CPUs are there, how many memory is there, and so on. But these are things we also will look a little bit more in lecture 5 then. The same is true when we look on the Hadoop distributed file system and also the Amazon services, just to actually let you know that, of course, it's not only Microsoft Azure that has Spark. You find also in the Amazon stack Elastic MapReduce, right, which is Hadoop. And if you look inside, it's really Apache Spark, Hive, and other big data frameworks that you actually have there as a kind of ecosystem around it. And you see essentially in the use cases, you cover almost everything big data analytics has to offer today to customers, from Elasticsearch over to small dashboards with QuickSight, or even, let's say, streaming again with having Amazon Kinesis, real-time analytics really fast, and so forth. But Elastic MapReduce is a service really that also is long-term already in the Amazon Web Services. And of course, this is just a service. Inherent, you have the hardware, and if you want to have Apache Spark, you want to spend money on memory capacity. So again, it will be costly. And with this, you better understand now our Chicago food. When we said like, okay, we start a Spark application. Now inherently, we said the Spark session is available. So this driver of Spark is ready to use all the different nodes. And you see also in the other previous lectures, or when you do it, you have an overview how many head nodes, how many worker nodes. And of course, this is something what we could configure. And this is just neatly now available in Jupyter, while under the hood, lots of things are happening line by line from Python, right? And PySpark is just giving you a very nice, let's say, Jupyter notebook optimized way how to do it and how to use it. Another example was then the dataset load, which is also something where you had basically different options in APIs. So Apache Spark is very strong in APIs. You would say today Pandas is also a very interesting API for this. We will explore this a little bit more on Thursday. But it has, let's say, something for untyped APIs where data frames exist a lot, but also very typed APIs where the data set is very clear, very structured. And this is really something what we used already when we read here basically the comma separated values from the food inspections, right? It created a Spark data frame, which is very optimized and inherently also supported by the RDDs structure of Apache Spark inherently. Right, when you now want to have a very good example, perhaps, of thinking about, now I have all this in Apache Spark, let's have a simple application. And this is loaded because in Hadoop times, you would have a word count, which means you have lots of source code to write a couple of lines. No, it's like, let's say, 2 functions, map and reduce, and you have, let's say, each of them have 20 source code lines. You have to think about the data, etc. And what you see here is really, in a way, you have this couple of 5 lines, and you can do word count, let's say, again, on a error log that you have on one of your web servers or on your game, whatever it is, the error and the log message you want to analyze. And you see here very much in parallel, this is done with a driver. It automatically assigns different workers that actually then is breaking down into different RDDs. And using here the transformations with the map that we already learned, breaking it line by line, so to speak, and distributing it over all the cluster and use a cache as much as possible. And then what we do with it, we have it now distributed. The action we really want to do is we want to count every occurrence of the word foo, every occurrence of the word bar. Of course, this could be the product of it could be the customer ID, whatever you want to analyze in your bugs and so on. But you can do this now in a really scalable fashion. The same is true, of course, with documents. You read them from a text file. You basically want to split them again, maybe on the /t to say line by line by line, and then distribute it over the whole cluster. And it's inherently totally independent parallel, so it could work on its own. And at the end, you get the count back by all of this, having it, very much kind of in a very nice style in a couple of lines parallelized. You see this here on the left-hand side. If you really put it to it, it's a couple of lines here, which previously takes, let's say, much more time to program and so forth. So this is, let's say, a real interesting example. Word count is always a, let's say, basic example of these big data analytics frameworks, if you will. For a more interesting relationship, again, between Spark and big data, I encourage you to look the video, basically, that you have here in the references. And that's all for part 1 in the moment. And we will continue with part 2 after 10 minutes.